a solid, and a liquid? Please welcome our winner.
Thank you. Thank you. So it's a great honor. It's very nice. So when I was asked if I was willing to accept the prize, the answer was easy. You know, it might be cool to refuse a Nobel Prize, but it's certainly uncool to refuse an Ig Nobel. So our cat's liquid. I saw this question asked on the internet, and it was based on the common definition that a liquid is a material that can adapt its shape to its container. And it seems to be the case. So I couldn't refrain from using this question as a way to highlight some of the actual questions and problems that are studied in rheology. So rheology is the study of flows, from the Greek rheo, to flow. You can find the same Greek root in the word diarrhea, so you know it's serious. And you can also find it in the more sophisticated word logorrhea, so I'll keep this short. So basically what I said in the paper is that Thank you, Miss Unikur. Thank you.
You can collect your $10 trillion from the Nobel laureates over there. The Peace Prize.
So is a cat a solid or a liquid? And his pictures, of course, make the argument that it's a liquid. And rheology is the study of flows. And rheology is kind of very interesting stuff. So when we talk about mechanics, we talk about classical mechanics, which is what we've been dealing with most of the semester. And then there is, so if we do that from that perspective, we get our statics, which is the study of equilibrium. We get dynamics, which is the study of motion. And then there's the lovely thing called fluid dynamics. And fluid dynamics provides us with a lot of different aspects. So one of the issues with fluid dynamics, and somebody had mentioned, let's go back to this, see if I can get the teacher camera back on, maybe. Let's see. Ah, good. So it'll be there in a second. There we go. So one of the things that we had talked to, somebody had mentioned when we were trying to get the description of the different phases on Wednesday, somebody had mentioned cornstarch, and I said cornstarch is interesting stuff. Because when we're talking with fluids and dealing with fluids, we think of water as a fluid, air can be a fluid, but fluids aren't necessarily all the same. So during the next week, you're going to experience the cornstarch fluid. And those of you who cook are aware that cornstarch does a lot of very magical things. If you've played with it, cornstarch makes oobleck, and people have heard of oobleck, right? Cornstarch, you can actually make it into a liquid, and if you play with it, you can run across it, and it becomes a solid. But when you put your hand in it slowly, it's a liquid. When you're getting ready to make your gravy, you can actually stir and make a cornstarch paste that will snap. But if you leave it alone, it's a fluid. What is happening with cornstarch, it's called a shear thickening fluid. So we discussed shear on Wednesday. Shear is that property where I'm taking and I'm applying a force like this. I'm applying a force along this line. Well, it turns out cornstarch is one of those weird things that if I do that, cornstarch will actually harden and become solid, or act like a solid instead of a liquid. And so it's considered a non-Newtonian fluid. because it doesn't behave like the fluids that we're about to talk about. It doesn't behave that way, and cornstarch happens to be, a cornstarch water mixture happens to be what we call a shear thickening fluid. We also are experiencing other non-Newtonian fluids that we get a lot. You don't necessarily think about it, but we can't have paint without a non-Newtonian fluid. So your good old house paint, your good old wall paint is a non-Newtonian fluid, except in that case, if I dip my brush in the paint and I pull it out, the paint's going to adhere to the brush. But when I put it against the wall and I apply that shear to it, it's a shear thinning fluid, and it allows me to get a thin coat of paint on the wall. So fluids are really cool. We also kind of mentioned that there were fluids that if I apply electric field to them, they're going to have different behaviors. They're non-Newtonian fluids. They're called electric rheological fluids. They're used in braking systems. They're used in a variety of different systems. And by applying an electric field to them, it's going to have that fluid behave more like that cornstarch fluid. I also have fluids that are called ferrofluids. Ferrofluids are ones that are affected by magnetic fields, and they're actually used for various seals and a variety of things. So fluids and fluid dynamics are really cool things, and we get a lot of interesting aspects. And so I know I have a couple of folks that are looking towards meteorology, and tornadoes are all fluid dynamics. So we get a variety of places where we get fluids and work with fluids. So thought that would be a good way to start a Friday before a long week, a long break, to look at the Ig Nobel with, kind of an interesting question. And that's, the Ig Nobels really do have some very interesting questions, and there's really practical science behind it. This one, of course, was tongue-in-cheek, but others are not. How much saliva does a child produce may or may not be a tongue-in-cheek, like, no pun intended. The piece of research. So we get, they're fun to go in and look at what gets the Ig Nobels. The other fun part is actually looking at what the name of the paper is. Because I've done a couple of columns about the names of the paper that you sit there and you'll read the paper and you go, okay, what are they thinking? And then when you get down to what the fundamental thing is, why can't they just say that, Why can't they just say that right out? They studied one is the production of, or whether or not certain compound in chocolate will produce myocardial infarction. Will it help produce or hinder a heart attack? All right, why do we have to do the whole thing? Does this compound help or hurt a heart attack? It's just scientific people sometimes have interesting approaches. So where we were on Wednesday is we had gotten through the bulk modulus, and we had looked at how things were compressible and what things were going to happen when we apply a force. But let's start.
Alcohol's got a black screen.
You got a black screen?
Yeah.
Let's see. Does that help? No. Because I should have the document camera. Let me come back out and put back up. No, they're not getting anything over there. There we go. Sometimes you just have to talk to it nice. Usually that's the first time I've had it happen that way. Usually what happens is you guys get the document camera and we don't get the document camera over here. So this is weird. So we got the document camera. Alright, so I'm going to give you a cube here. And this cube happens to be a 1 meter by 1 meter by 1 meter cube. So this is a meter cube. And we're going to give it a density of 7.86 times 10 to the third kilograms meters cubed. This happens to be the density for iron. Okay, that happens to be, oh, I'm all crooked and cockeyed, there we go. Now we won't make everybody all wonky. So that's a meter cubed. And if I put a meter cubed and I'm in a pool, and I take that meter cube, I'm gonna have to use a forklift, of course, right? Because that's 7,860 kilograms, which if you multiply by 2.2, right? It's gonna be a big cube. But if I took it over with my forklift and I took it to the pool, and I set it into the pool, what's gonna happen?
In a melt? Or is it ice?
It's iron.
Iron? Oh, it's gonna sink?
It's gonna sink. It's totally gonna sink. Now think about that for a second. I put 1 cubic block of iron in the pool. Alright, took 1 cubic block of iron in the pool. So I'm gonna switch, I'm gonna tempt fates and I'm gonna go back and forth. This is gonna be an interesting day. Tempting fates. Okay, let's see if I can boom it down a little bit. Let me just save the jazz and come up with a different. Okay, go over here to file. Pop up in my downloads. Open the pictures. Okay, maybe, there it is. Maybe. Just thinking about it.
Polar Endeavor. I only got a picture on there.
There we go.
There it is.
Alright, so you guys can see that is a crude oil carrying vessel. Now we just said that if I had 1 meter cubed of steel, it's going to sink. Well, that sucker weighs a whole lot more than 7,860 kilograms. Why doesn't it sink? Okay, it doesn't sink. But we know that steel has a density that if I put it, it's going to sink. But I can make a boat. I can make a boat. And in fact, I think I even have the specifications. Because that's why I put it in there. I love specifications. So if you go and you look at the specifications, the Polar Endeavor and the Polar, it's a double hull tank ship that weighs 141 dry tons. 141,000 dry tons. So why doesn't it sink? It doesn't sink because of something called Archimedes' principle. It doesn't sink because of Archimedes' principle. And if you start thinking about it, that's kind of an interesting idea because we've known about things don't sink. Or we get things that don't sink. Now we can make it sink, right? We can totally make it sink. I don't want the mobile device, I want the document camera. We're attempting fates, we're going back to the document camera. There we go. Okay, so I can, if I take this cubic meter of iron and I create a shell, like making a ship, and I happen to make my shell like this, where this is 3 meters by 3 meters by 6 meters, it still has the same mass, but the volume now is 3 times 3 times 6, which is going to give me 54 cubic meters. And at that point, it's going to float. Because Archimedes' principle says, and this is good old Archimedes, remember Archimedes was a Greek. He said that any object completely or partially submerged. And we put that right there, submerged in a fluid is buoyed up by a force with a magnitude equal to the weight of the fluid displaced. I'm going to move it up here just a second. So Archimedes' principle says that any object completely or partially submerged in a fluid is buoyed up with a force with a magnitude equal to the weight of the fluid displaced. So by changing the dimensions, I'm changing how much fluid is displaced. And by doing that, if I get a thin shell, I can actually have a ship float. We can actually have a ship float, and we can look at that aspect. So, in Blackboard, I've done this problem several times because the best way to look at this problem is to look at it through an iceberg. We look at it through an iceberg. And so what we can do there, by the way, I'm using reusable paper. In my other physics class, I went in and I did this and they went, what? It's essentially a sheet of erasable paper. And I can erase it. But it was funny when I did it in my afternoon class.
They weren't used to you having it.
No, they weren't. They didn't have it. That was like, oh, okay. That was just a little weird. There was a little bit of shock and awe. It was kind of fun. So let's take an iceberg here. So I got an iceberg, and we all know the rules, right? How much of the iceberg is typically exposed?
10%.
About 10%. We've got that, we've been told for years and years and years it's about 10%. Well, we're about to prove it. Okay, we're about to prove it. Because the density of ice is 917 kilograms per meter cubed. The density of seawater is equal to 1,030 kilograms per meters cubed. So I do have a difference of density between ice and seawater. And so if you go up and you look at a typical mass of an iceberg, the mass of this iceberg that we're going to use is 100,000 kilograms. So we want to know what percent of the iceberg is above the water. That's what we really want to know, is what percent of the iceberg is above the water. So the first thing I got to do is calculate the volume of the iceberg. So volume, if we remember that density is mass per unit volume, the volume is going to be mass divided by the density. Okay, mass divided by the density, and that's going to be my 100,000 kilograms divided by the density of ice, which is 917 kilograms meters cubed. It's going to give me 109 meters cubed. So that's the volume of my iceberg. Now Archimedes' principle says that the mass of the fluid displaced is going to be, our volume of fluid displaced is going to be related to its density. So the volume of seawater is going to still be the mass of the iceberg.
We're not seeing part of it.
There we go. It's a reflection. It's going to be the same volume or same mass, but this time I'm going to use the density of seawater. And that's going to give me 97 meters cubed. So in the case of my iceberg, I'm going to be displacing 97 cubic meters of seawater, but the volume of the iceberg is 109 cubic meters.
Salt base.
The density, the density, this is the density of seawater, this is the density of ice.
Oh, you.
We get the density of seawater and the density of ice. So the amount of the iceberg that's above the water is 109 meters cubed minus 97 meters cubed, and that's going to give me about 12 meters cubed. And if I take that 12 meters cubed and I divide it by the volume of the iceberg, that tells me it's roughly 11% of the iceberg that's above the surface of the water. So it's when we deal with these things, we get a buoyant force that's equal to the volume of the water displaced. So so if we go back and we look at why, go back here for a second and look at why the block sinks. So if I have my block of iron, there's my block of iron, and it has a mass of 9, or what do we say? It has a density of 760 kilograms per meter cubed. That's its density. The density of water, this is fresh water. That's the density of fresh water. I end up with my block sinking. Okay, I end up with my block sinking. But if I use the shell, we did our shell here, that's going to be 54 meters cubed. So the amount of water this shell can be displacing is 54,000 kilograms. So of course it's going to float. Of course it's going to float. Because I could be displacing up to 54,000 kilograms. Now the fun part is, using this, just how high above the water is it going to be? Because we need the mass of the water displaced needs to be 78, 60. So if I want to figure out the height of this side where the water level is going to be, what I would do is do the exact same thing I did with the iceberg. I'm going to figure out my area, let's go ahead and figure that out. So if I do my 78, 60 kilograms, my density of water is 1,000 kilograms per meters cubed, which is going to tell me that's going to be 7.86 meters cubed. And we said that this was 3 high, we said this was 3 wide, and we said this was 6 long. So area times height is going to be my volume, which we said is 7.86. So height is going to be my 7.86 meters cubed divided by my area, which is 6 times 3, and that's meters squared. This gives me 0.437 meters or it's going to be about 44 centimeters up the wall. So I'm going to have a lot of my shell above the surface of the water. So that's why Archimedes' principles works. That's why we actually can deal with the mass, because basically when you do the weight of a person, so here's my block, and I put this on a scale, a good old fish scale, you could actually measure your buoyant force. At least in water. You can measure your buoyant force because that scale is going to look differently outside of the water, because the force that you're going to read on the scale is going to be the force due to gravity minus the force buoyant is going to equal the reading on the scale. Because I've got a buoyant force pushing up, I've got gravity pushing down. The difference of that is what's going to be the reading on the scale. And if I put it in oil, it's going to be different than if I put it in water, which is going to be different than if I put it in nublic, or put it in slime, or put it in Jello. Although Jello is kind of not a fluid. Jello is sort of a solid. Now, of course, you can't put it, well, you could put it in a cat, just that you got to make the cat eat it. So we get some interesting pieces there. So that's Archimedes' principle. We talked about Pascal's principle, because the three big principles that we work with in all of this, the three big principles that we work with are Pascal's, and he's the one that says that my fluid, that the pressure is going to be distributed over the course of my container. Archimedes is going to give me the one that I'm worried about the force on my scale. And then we get, okay, if I can spell it out right, we get good old Bernoulli. Now Bernoulli gives us the idea that if I have fluid flow, that my fluid is going to have to flow through the pipe. And if I look at this, the mass that's going through here has to equal the same mass that's going there. Otherwise, I'm going to burst my tube. Otherwise, I'm going to burst my tube. So we've all done this. How many of you have put your thumb over the hose, the water coming out of the hose? Okay, we've all done it. What happens to the water when it comes out of the hose?
Comes out faster.
It comes out faster. I end up having to have a different velocity here than I have a velocity there. We end up doing it, for those of you medical types, this is the idea of a syringe. Same thing. We end up with a syringe. We get it. And basically what Bernoulli's principle is going to allow us is that the area 1 times the velocity 1 has got to equal area 2, velocity 2. Because this is related to the mass flow, how much mass am I getting there, and how much mass is over there. We can actually calculate the differences in the body. It also results in a change in pressure. Okay, it also results in a change in pressure, and so we can get what we call the overall Bernoulli equation. And we can do it by using conservation of energy, but I'm just going to write it down. That the pressure plus 1/2 the density times velocity squared, looks like kinetic energy, right? Plus the mass times gravity times my change in height, which is going to be my potential energy, is going to equal some constant. And I'm about to show you a video that helps explain this a lot better, because it's going to walk through all of it with a kind of an animation of what the fluid is doing. Now this means that if I do this as pressure 1, velocity 1, height 1, I can equal pressure 2 plus the density velocity 2 squared plus mgy2. And what we end up doing all the time when we use this equation is we cancel things out. So if I'm at constant pressure, guess what? I can cancel out pressure. If I'm at constant height, I can cancel out height. I only have to worry about the various pieces to get there. But what this ultimately tells you is that I'm going to get a change in pressure that goes through the pipe. And you can actually measure this by putting a pressure monitor on this side of the pipe and a pressure monitor on that side of the pipe. And that's ultimately going to give us why an airfoil is going to, so if I have my air flowing over my airfoil, and how that works, because of that difference in pressure, the pressure up here is lighter than the pressure here, which is going to cause my airfoil to move up, which is going to give me what we call lift, which is what's going to allow an airplane, a heavier than air object, to be able to fly through the air. And it's the result of this change in pressure that we get out of the Bernoulli equation. So I'm going to switch back over here, because I have it posted. We will go in there and do it. So I'm going to come over here, we're going to do the desktop computer. I have added to, I was playing with it. In Blackboard, so if you go back into Blackboard, and you guys can see it now over there. In week 14, I cleaned it up just a little bit. There's a week 15. I cleaned it up because I ended up having this one like 4 times in here, and it only needs to be there once. I did add the organic tutor that walks through the development of the Bernoulli equation. So I added that this morning, and I added the link for the ignoble cats. So that you can actually look at it. But if you want to see the flows, these because they terminated the channel. Bummer. But you can actually look. There's a whole bunch of World War II training videos, and they have these that you can actually look at them and find them. So I guess I need to get rid of it because those are smoke tests and they went away. Bummer. But the vintage wind tunnel test, some of the World War II training videos have a lot of interesting pieces in doing the animations. But we're going to look at this one, the applying medicine, so I'm going to go full screen.
This is lesson 7 on fluid mechanics and medicine, and the topic is the Bernoulli equation. The learning objective is to be familiar with some of the diverse applications of the Bernoulli equation and to be aware of the Venturian effect. In the last lesson on the continuity equation, we started with a fluid conduit of variable cross-sectional area in which some non-compressible liquid was traveling left to right. And we looked at how the product of the cross-sectional area and the velocity in one segment must be equal to the product of the cross-sectional area and the velocity in another segment. For the Bernoulli equation, we're not directly interested in the cross-sectional area in each segment anymore, but rather the velocities, the pressure, and the height of the fluid above some arbitrary zero level. In the interest of time, I'll spare you its derivation and just give the Bernoulli equation to you. The pressure at point 1 plus 1/2 the fluid density times the velocity at point 1 squared plus the density times little g times the height at point 1 must equal the sum of those same values at point 2. Or another conceptually identical version states that this sum is a constant. This equation may look a little unwieldy until you realize that just as the continuity equation is nothing more than the law of conservation of mass as applied to fluids, the Bernoulli equation is the law of conservation of mechanical energy applied to fluids. This term is the potential energy density of the fluid. This term is the kinetic energy density of the fluid. And this term is something called pressure energy density. Don't worry if the term pressure energy is totally unfamiliar to you. Just know that as a liquid travels through a conduit, these various energies trade off at different points, but their sum is always the same. For the rest of the video, I'll go through two rather different examples of how to apply the Bernoulli equation. First, imagine we have a bucket on top of a marble block. If a hole is drilled at the bottom of a full bucket of water, whose height is h, what velocity will the water have when it initially exits the hole? This problem may seem unexpected at first, since a bucket of seemingly stationary water looks quite different than the conduit I referred to a second ago. However, the water in the bucket is not stationary after all, and the bucket is just an unusually shaped conduit. Let's start by writing out the full Bernoulli equation. Next, we need to define a point 1 and a point 2. One of these will obviously be the exit hole, and the other should be a location where we know the most information. In this case, it's the top of the barrel at the water line. So there are points 1 and 2, which makes this velocity v2. So how can we substitute in for the missing variables? First, the pressure of point 1 is atmospheric pressure. What is the velocity of point 1? By the continuity equation, the velocity times cross-sectional area at point 1 must equal the velocity times cross-sectional area at point 2. However, if we assume that the cross-sectional area of the entire barrel is much, much larger than that of the hole, the velocity at point 1, that is how fast the water line is moving down, is very, very small, and for practical purposes can be assumed to be 0. The value of y1 is the height of point 1 above some arbitrary level. We can make that arbitrary level anything, but let's make it the top of the marble block. So y1 becomes h. Next we have p2. This may or may not seem intuitive, but if point 2 is located just at the lip of the exit hole, the water here is also exposed to atmospheric pressure. So p2 is also p atmosphere. v2 is of course what we are solving for, and y2, or the height of point 2 above the top of the marble block, is 0. So p atmosphere cancels out, and this term is 0, as is this one. This gives us density times little g times h equals 1/2 density times v2 squared. Densities cancel, and solving for v2, we find that it is equal to the square root of 2 times little g times h.
And you've seen that one.
There are a number of fascinating things about this rather elegant solution. First, the velocity of the fluid coming out is independent of its density. Whether it's water or mercury, the velocity will be the same. Next, the width of the barrel and the width of the hole are both irrelevant, provided that the barrel is many times larger than the hole. Finally, and most interestingly, this is the same velocity that an object or fluid would have as it passed point 2 if dropped from an h and allowed to fall straight down under the influence of just gravity. This is historical trivia, but this solution is called Torricelli's theorem. Torricelli is the 17th century Italian physicist who invented the barometer and for whom the unit of torr is named after. Let's look at another application of the Bernoulli equation, one that's a bit more complicated. Here's a schematic of an interesting contraption called a Venturi meter. It consists of a horizontal tube of 2 different widths, where a vertical tube is attached to both the wide section and narrow section. A fluid moves along its length. You've probably already noticed something interesting. The height of the vertical columns of fluid are not equal. This might seem to be a violation of the principle discussed in the lesson on hydrostatics, that fluids always seek their own level, but that only strictly applies to stationary fluids. This is an example of the Venturi effect in which the pressure in a fluid moving through a conduit is decreased when the fluid flows through a constricted section. The term Venturi effect is also occasionally used more broadly for a variety of related phenomenon, particularly in medicine. How could we analyze this situation quantitatively? Suppose we can measure the height difference between the two columns, which we will call h. Given only A1, A2, and h, what is V1 and V2? I can imagine this seeming like a profoundly difficult problem, but I guarantee you that we have already covered all of the tools necessary to solve it within this video series. So let's start with the complete Bernoulli equation. We see that although the pressures, that is P1 and P2, are neither given to us nor requested as part of the solution, we'll still need to include them along the way. The first simplifying step is to realize that the vertical height of the two sections is the same, so these terms cancel out. With a little rearrangement of the remaining terms, we are left with P1 minus P2 equals 1/2 the density velocity 2 squared minus half density velocity 1 squared. Factoring out the 1/2 in density gives us this, which is looking more manageable. But where do we go from here? The first trick is to realize that in order to get rid of the unknown P1 and P2, we will need to use our knowledge of hydrostatics, and we'll need to define, at least temporarily, a different height, that is the height from the center of the main horizontal conduit to the top of the lower of the two vertical fluid columns. I'm going to call this H prime. How does defining H prime help? We know from hydrostatics that the hydrostatic pressure is density times little g times the height of the overlying fluid. So P1 is equal to density times little g times the sum of H and H prime. The same rationale allows us to state that P2 is equal to density times little g times H prime. And the simple but nevertheless cool algebraic trick allows us to simply subtract one equation from the other, giving us this. P1 minus P2 equals density times g times H. And we can substitute that right in here. The next major trick to achieving the solution to this problem is to remember the continuity equation. A1 times B1 equals A2 times B2. Solve for B2 and substitute that in here. And with these two substitutions, we are left with this. Density cancels, and everything that is left is either given or is what we are solving for. At this point, we leave physics behind and concentrate just on the algebra. Multiply both sides of the equation by 2, factor out the V1 squared, and solve for V1. To arrive at an expression for V2, substitute all of this back into the continuity equation. This answer might initially look ugly and cumbersome, but I actually find it kind of awesome that the velocity of fluid moving through this tube can be determined from the ratio of the cross-sectional areas and the difference in column height. That's it for Bernoulli and Venturi in physics. The next video will cover 2 examples of using these principles in medicine.
Yeah, so for you medicine types, you can go back to that video and then look at the other aspects. But if you start thinking about it, you're looking at fluid flow and blood vessels, arteries, going through valves in the heart. So you get a lot of the Bernoulli equation is a critical piece. So we are now done with chapter 9, and that gets us to what we have left. What we have left, I'm going to go this way. Let's do that. So what we have left is thermodynamics, which we will cover on next week after we come back from Thanksgiving. If I do that. Okay. See what you got. And for those of you in Tonkawa, I will have, if you didn't get your test before, I will have those, because your best study guide for the final is going to be your previous tests. So that will be your best study guide. Make sure that I think it's like a lot of the homework is due the Wednesday of the week after Thanksgiving. So you want to make sure that you get that in there, and as soon as I get the stuff from Dr. Salamanu, I will get the grades in on this side. I am on the Enid campus all day today. I have an appointment at 2:30, so if anybody wants to catch me, they can. And I'll let you guys go. Have a great Thanksgiving.